Hello there, and welcome to the Sleepy Science channel. Tonight, we are going to explore something truly extraordinary, something invisible yet everywhere, something that shapes galaxies, bends light, and holds the universe together. Yet, we have never seen it directly. We are going to drift through the mysterious realm of dark matter, that hidden scaffolding upon which all visible creation rests. Above us and around us and through us flows a substance we cannot touch or see. It does not glow, it does not shine, it does not reflect light or give off heat, and yet without it, galaxies would fly apart, stars would never have formed, and we would not be here to wonder about it." End quote. End quote. Dark matter is one of the most profound mysteries in all of science, a riddle written into the very fabric of existence. It makes up most of the matter in the universe, far more than all the stars and planets and gas clouds combined. Yet it remains hidden from our eyes, invisible to every form of light we know. If you enjoy these quiet explorations into the cosmos, I invite you to like and subscribe, or share a simple thought down in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is rest, settle in, and allow the calm of the cosmos to carry you. Let the mystery of dark matter wash over you like a gentle tide. And let's begin. Dark matter makes up about 85% of all matter in the universe. When astronomers calculate the total mass of everything that exists, they find something astonishing. All the stars we see, all the galaxies, all the planets and moons and nebulae, all the dust and gas scattered across space, these things together account for only about 15% of the matter in the universe. The rest, the vast majority, is dark matter. It does not emit light. It does not absorb light. It does not reflect light. It interacts with the universe almost entirely through gravity. This means that most of the universe is made of something we have never directly observed. Something we know exists only because of how it pulls on the things we can see. Imagine a cosmic ocean where the waves and foam we observe represent just a fraction of the water beneath. Dark matter is that hidden depth, silent and unseen, yet holding everything afloat. We live in a universe where the visible is the exception and the invisible is the rule, where the substance that shapes galaxies and clusters of galaxies remains one of the greatest mysteries we have ever encountered. And that mystery surrounds us always, flowing through space, flowing through us, unnoticed, but ever present. Dark matter was first proposed in the 1930s by an astronomer named Fritz Zwicky. Zwicky was studying a cluster of galaxies called the Coma cluster. He noticed something strange. The galaxies in the cluster were moving far too fast. According to the laws of gravity, they should have flown apart long ago. The visible matter in the cluster was not enough to hold them together. Yet there they were, bound in a stable group. Zwicky calculated that there must be far more mass present than anyone could see. He called this unseen mass dark matter. At the time, his idea was largely ignored. It seemed too radical, too strange. But Zwicky was right. What he glimpsed in those fast-moving galaxies was the first hint of a hidden universe, a realm of matter that does not shine but shapes everything we see. His discovery was like finding the skeleton of the cosmos, the invisible structure that holds the body of the universe together. Today we honor Zwicky as a pioneer, a scientist who looked beyond the visible and asked what else might be out there. His question opened a door that has never closed. Decades later, astronomer Vera Rubin confirmed dark matter's existence through her studies of rotating galaxies. In the 1970s, Vera Rubin and her colleague Kent Ford carefully measured how fast stars were moving in spiral galaxies. They expected to find that stars farther from the galactic center would move more slowly, just as planets farther from the Sun orbit more slowly. But that is not what they found. Instead, stars at the outer edges of galaxies were moving just as fast as those closer in, sometimes even faster. This should not have been possible. The visible matter in those galaxies was not enough to generate the gravity needed to keep those outer stars in orbit. They should have been flung out into space, but they were not. Rubin realized that there must be vast halos of invisible matter surrounding these galaxies, matter that extended far beyond the visible stars and gas. This dark matter provided the extra gravity needed to hold everything together. Her work transformed our understanding of galaxies. She showed that what we see is only a small island of light floating in a much larger ocean of darkness. Rubin's careful observations gave us one of the clearest proofs that dark matter is real. Her legacy is a reminder that sometimes the most important discoveries come not from seeing new things, but from measuring the old things more carefully. From asking why what we observe does not match what we expect, and from having the courage to accept that the universe is stranger than it appears. Dark matter does not interact with light in any way we can detect. One of the most puzzling things about dark matter is its relationship with light, or rather, its lack of one. Light is made of particles called photons. When photons encounter normal matter, they interact. They bounce off surfaces. They get absorbed by atoms. They scatter through gases. This is why we can see ordinary matter. It glows, reflects, or blocks light. But dark matter does none of these things. Photons pass right through it as if it were not there. This makes dark matter completely invisible. No telescope, no matter how powerful, can capture an image of it directly. It does not glow in visible light. It does not shine in infrared or ultraviolet or X-rays or gamma rays. It is silent across the entire electromagnetic spectrum, and yet we know it is there because of how it bends space itself. Dark matter may not interact with light, but it does interact with gravity, and gravity bends the path of light. So while we cannot see dark matter directly, we can see its shadow, its influence, its fingerprint on the fabric of the universe. It is like knowing the wind exists, not by seeing it, but by watching the trees sway. Scientists detect dark matter by observing how it affects visible matter. Since dark matter does not emit or absorb light, scientists must rely on indirect methods to study it. They watch how galaxies rotate, how clusters of galaxies move, how light bends as it passes near massive objects. All of these observations reveal the presence of something unseen, something with mass and gravity but no light. One method involves studying gravitational lensing. When light from a distant galaxy passes near a massive object, the gravity of that object bends the light's path. This causes the distant galaxy to appear distorted or magnified. By measuring these distortions, astronomers can map the distribution of mass along the line of sight. Often they find far more mass than can be accounted for by visible matter alone. That extra mass is dark matter. Another method involves measuring the motion of stars and gas in galaxies. By observing how fast things are moving, scientists can calculate how much mass is present. Time and again, the answer comes back the same. There is far more mass than we can see. Dark matter also leaves its mark on the cosmic microwave background, the faint afterglow of the Big Bang. Tiny fluctuations in this ancient light reveal how matter was distributed in the early universe, and those patterns match what we would expect if most of the matter were dark. Every method points to the same conclusion. The universe is filled with something we cannot see, but whose presence is undeniable. We live in a cosmos where absence speaks as loudly as presence, where the invisible shapes the visible, and where mystery is woven into the very structure of reality. Dark matter forms vast halos around galaxies. When we look at a spiral galaxy like our own Milky Way, we see a bright disk of stars, a glowing core, spiral arms stretching outward. But this visible structure is only a small part of the whole. Surrounding the galaxy is an enormous halo of dark matter. This halo extends far beyond the visible edge of the galaxy, in some cases 10 times farther or more. It is roughly spherical, enveloping the galaxy like an invisible cocoon. The mass of this dark matter halo is far greater than the mass of all the stars, gas, and dust combined. In fact, for every kilogram of ordinary matter in a galaxy, there may be 5 or 6 kilograms of dark matter. This halo provides the gravitational scaffolding that holds the galaxy together. Without it, the stars would drift apart. The galaxy would dissolve. The dark matter halo is also thought to play a role in how galaxies form and evolve. It acts as a gravitational anchor, drawing in gas and dust, helping to trigger star formation. It shapes the rotation of the galaxy, and it influences how galaxies interact with one another. In a sense, the galaxy we see is just the bright tip of a much larger, invisible structure. A lantern glowing inside a vast dark room. The halo is the room, silent, unseen, but essential. Without dark matter, galaxies as we know them could not exist. The universe would be a very different place. Dimmer, emptier, less structured. Dark matter is the hidden foundation upon which all visible structure rests. Galaxy clusters are held together by dark matter's gravity. On an even larger scale, dark matter shapes not just individual galaxies, but entire clusters of galaxies. These clusters are some of the largest structures in the universe, containing hundreds or even thousands of galaxies, all bound together by gravity. When astronomers study these clusters, they find the same pattern. The visible matter, the galaxies themselves, is not enough to hold the cluster together. The galaxies are moving too fast. They should escape, but they do not. There must be additional mass, additional gravity. That mass is dark matter. In fact, in galaxy clusters, dark matter can make up as much as 85 to 90% of the total mass. It forms a vast web of invisible structure, threading through the cluster, binding the galaxies together. Telescopes that can detect X-rays reveal hot gas filling the space between galaxies in a cluster. This gas is also held in place by the gravity of dark matter. By studying the temperature and distribution of this gas, scientists can infer the distribution of dark matter around it. The more dark matter present, the stronger the gravitational pull, and the hotter and denser the gas becomes. Dark matter does not just fill the space around galaxies. It weaves through the entire cosmic web, the large-scale structure of the universe itself, stretching across millions and billions of light years. It is the glue that holds the universe together, the unseen architect of cosmic structure. The cosmic web is a vast network of dark matter filaments. If you could see the universe on the largest scales, you would see something remarkable. Galaxies are not scattered randomly through space. They are arranged in a vast web-like pattern, long filaments of galaxies stretching across the cosmos, connected by nodes and clusters. And between these filaments, vast empty voids. This structure is known as the cosmic web, and it is shaped primarily by dark matter. In the early universe, dark matter began to clump together under its own gravity. These clumps formed the seeds around which normal matter, hydrogen and helium gas, would later collect. Over billions of years, this process created the filaments and nodes we see today. Dark matter forms the backbone of the cosmic web, the invisible threads that connect galaxy clusters and superclusters. Normal matter follows these threads, flowing along the dark matter filaments like water along the cracks in a sidewalk. The cosmic web is one of the most beautiful structures in the universe, a delicate lacework of light and shadow, of matter and void, stretching across billions of light years. And at its heart, shaping every strand, is dark matter, the invisible hand that guides the architecture of creation. Simulations of the universe's evolution rely on dark matter to match observations. Scientists use powerful computers to simulate the history of the universe. They start with the conditions shortly after the Big Bang. Then they let the simulation run forward, allowing gravity to pull matter together, stars and galaxies to form, structures to grow and evolve. When they run these simulations without dark matter, the results do not match what we see in the real universe. Galaxies form too slowly. Galaxy clusters do not hold together. The cosmic web does not appear. But when they include dark matter in the simulation, everything changes. The universe that emerges looks just like the one we observe. Galaxies rotate the way Vera Rubin measured. Clusters hold together the way Fritz Zwicky predicted. The cosmic web forms with its filaments and voids. The simulations match reality beautifully. This is one of the strongest pieces of evidence for dark matter. Not only do we see its effects in observations, but we can reproduce those effects in simulations. We can build a model universe, watch it evolve, and see dark matter shaping it in exactly the way it shapes our own universe. It is a kind of cosmic confirmation, a consistency between theory and observation that gives scientists confidence. Dark matter is not just a hypothesis, it is a necessary ingredient. Without it, the universe we live in could not have formed. The largest colliding galaxy clusters reveal dark matter's presence. One of the most striking pieces of evidence for dark matter comes from studying collisions between galaxy clusters. When two massive clusters collide, the event unfolds over millions of years. The galaxies themselves, being mostly empty space, pass through one another relatively unscathed. But the hot gas in each cluster, which makes up most of the normal matter, collides and slows down. It creates a shock wave, glowing brightly in X-rays. Dark matter, however, does not collide. It does not interact with itself in the same way. It passes right through. This creates a strange and revealing situation. After the collision, the visible gas ends up in one location, but the majority of the mass, detected through gravitational lensing, ends up somewhere else. The mass and the light are separated. This separation is powerful evidence that most of the mass is not in the form of normal matter. It is dark matter. One of the most famous examples of this is the Bullet Cluster, two galaxy clusters that collided about 150 million years ago. Observations show that the hot gas, visible in X-rays, is concentrated in the middle. But the gravitational lensing, which reveals where the mass actually is, shows that most of the mass is farther out, separated from the gas. This is exactly what we would expect if dark matter exists. It is like watching a ghost walk through a wall. You cannot see the ghost, but you can see the wall move. Dark matter does not emit heat or electromagnetic radiation. Unlike normal matter, which glows and radiates energy across the spectrum, dark matter is completely dark. It does not produce heat. It does not generate electromagnetic radiation. Not visible light. Not infrared. Not radio waves. Not X-rays. Nothing. This makes it profoundly different from the matter we are familiar with. Every atom in your body, every star in the sky, every planet and moon and grain of dust, all of these are made of particles that interact with photons. They absorb and emit light. They can be heated and cooled. They radiate energy. But dark matter does none of this. It is inert to light, to heat, to all forms of electromagnetic interaction. This is why we cannot see it with telescopes, why we cannot feel it, why it passes through us without leaving a trace. And yet it is there, all around us, permeating space, drifting through the earth, flowing through our bodies. We are immersed in an ocean of dark matter at every moment, but we never notice. It is like living inside a shadow that has substance but no form, mass but no light, presence but no touch. The silence of dark matter is absolute. It is a cosmic mystery wrapped in invisibility, a reminder that the universe is full of things we cannot perceive, things that exist beyond the reach of our senses, and yet shape everything we know. Scientists are searching for dark matter particles on Earth. Although dark matter does not interact with light, scientists hope it might interact, very rarely, with normal matter. Deep underground, in mines and tunnels far from the interference of cosmic rays, researchers have built detectors designed to catch dark matter particles. These detectors are incredibly sensitive. They wait for a dark matter particle to bump into an atomic nucleus in the detector. Such an event would be incredibly rare, but if it happens, it would produce a tiny flash of light or a small amount of heat, something the detector can measure. Experiments like these have been running for years. Some use liquid xenon. Others use crystals, cooled to near absolute zero. Others use different materials. All of them are shielded from outside interference. Buried deep underground to block cosmic rays, kept as quiet and still as possible. So far, no experiment has definitively detected a dark matter particle, but the search continues. Each experiment rules out certain possibilities, narrowing down what dark matter could be. It is a slow and painstaking process, a cosmic game of hide and seek played in the depths of the Earth. And though we have not yet found the particle, every experiment brings us closer, teaching us more about what dark matter is not, and guiding us toward what it might be. Dark matter may consist of WIMPs, or weakly interacting massive particles. One of the leading candidates for dark matter is a type of particle called a WIMP, weakly interacting massive particle. These hypothetical particles would have mass, enough to account for the gravitational effects we observe. But they would interact with normal matter only through gravity and possibly the weak nuclear force, one of the four fundamental forces of nature. This would make them extremely difficult to detect. They would pass through ordinary matter, almost as if it were not there. Only very occasionally would a WIMP collide with a normal particle. WIMPs are predicted by some theories of particle physics, particularly theories that extend the Standard Model, the current best description of particle physics. If WIMPs exist, they would have been created in the early universe, shortly after the Big Bang. As the universe cooled, these particles would have frozen out of the hot plasma, leaving behind a vast population of them scattered throughout space. Over billions of years, they would have clumped together under gravity, forming the halos and filaments we observe today. Despite decades of searching, WIMPs have not yet been detected. But that does not mean they do not exist. It may simply mean they are even more elusive than we thought, or that our detectors are not yet sensitive enough. The search for WIMPs is one of the great experimental challenges of modern physics, a quest to find a particle that hides in plain sight, that fills the universe yet leaves almost no trace. Axions are another candidate for dark matter particles. While WIMPs are heavy and slow, axions would be the opposite, extremely light, incredibly abundant, and moving very fast. Axions were originally proposed to solve a different problem in particle physics, but scientists soon realized they could also make good dark matter candidates. If axions exist, there would be trillions upon trillions of them passing through every square centimeter of space every second. They would form a vast cosmic fog, filling the universe, invisible and nearly massless. But, collectively, their mass would add up. Unlike WIMPs, Axions would not interact through the weak nuclear force. Instead, they might interact very weakly with magnetic fields. Scientists are building experiments to detect this interaction. These experiments use powerful magnets and sensitive instruments, trying to catch the faint signal of axions converting into photons in the presence of a magnetic field. So far, axions have not been found, but the search is ongoing, and the possibilities are tantalizing. If axions are real, they represent a completely new kind of particle, something beyond the standard model, a window into physics we have not yet explored. Whether dark matter is made of WIMPs, axions, or something else entirely, the search continues. And with each experiment, each observation, each calculation, we come a little closer to solving one of the greatest mysteries in all of science. Some theories propose dark matter is made of primordial black holes. Not all dark matter candidates are exotic particles. Some scientists have suggested that dark matter could be made of black holes. Not the black holes formed from collapsing stars, but much smaller, primordial black holes. These would have formed in the very early universe, shortly after the Big Bang, when the density of matter was incredibly high. If certain conditions were met, tiny regions of space could have collapsed directly into black holes. Some of these primordial black holes could be very small, perhaps no larger than a grain of sand, but with the mass of a mountain. Others could be larger. These black holes would not emit light. They would interact only through gravity, just like dark matter. And they would have been scattered throughout the universe as it expanded. For a time, primordial black holes were considered a strong candidate for dark matter, but recent observations have placed tight constraints on this idea. Studies of gravitational lensing, the bending of light by massive objects, suggest that if dark matter were made of black holes, we would see certain effects that we do not observe. This does not rule out primordial black holes entirely, but it makes them less likely. Still, the idea remains intriguing, a reminder that dark matter could be something entirely different from what we expect. Something hidden not in the quantum realm but in the warping of space and time itself. Dark matter does not clump as tightly as normal matter. One of the key differences between dark matter and normal matter is how they behave under gravity. Normal matter can clump very tightly. It forms stars, planets, dense clouds of gas. It can collapse into compact objects. This is because normal matter can lose energy. When particles collide, they can emit radiation. This carries energy away, allowing the matter to cool and condense. But dark matter does not do this. It does not interact with light or radiation. So when dark matter particles pass through each other, they do not lose energy. They cannot cool. They cannot collapse into tight clumps. Instead, dark matter remains spread out, forming large, diffuse halos. This is why dark matter forms halos around galaxies rather than collapsing into the galactic disk. It is why dark matter filaments stretch across vast distances without breaking into smaller pieces. This property also affects the formation of structure in the universe. In the early universe, dark matter began clumping together first, creating gravitational wells into which normal matter could fall. But because dark matter cannot cool and condense, it sets a limit on how tightly structures can form. This difference between dark and normal matter is subtle but profound. It shapes the way galaxies evolve, the way stars form, the way the cosmic web is structured. It is a reminder that dark matter is not just invisible normal matter. It is something fundamentally different, governed by different rules, shaped by different forces, a substance that exists in a realm just beyond our full understanding. The presence of dark matter affects the rotation curves of galaxies. When astronomers measure how fast stars and gas are moving in a galaxy, they plot what is called a rotation curve. This is a graph showing orbital speed versus distance from the galactic center. For a galaxy made only of visible matter, we would expect the rotation curve to drop off at large distances, just as planets farther from the Sun move more slowly. But that is not what we see. Instead, the rotation curves of galaxies remain flat or even rise slightly, out to the very edges of the galaxy. This tells us there is additional mass present, mass that extends far beyond the visible stars and gas. That mass is dark matter. The flat rotation curves are one of the clearest and most direct pieces of evidence for dark matter. They show that galaxies are embedded in massive halos of unseen matter, halos that extend far into space, holding the outer stars in their orbits. Without dark matter, these stars would fly away. The galaxy would unravel. But the dark matter holds it together, like an invisible hand, gently guiding the motion of every star. Vera Rubin's discovery of flat rotation curves revolutionized our understanding of galaxies. It revealed that what we see is not all there is, that the universe has layers, depths, hidden dimensions of matter and mass. And it set us on a path toward one of the greatest mysteries in science, a mystery that continues to unfold with every observation, every experiment, every new piece of data we gather. Dark matter played a crucial role in the formation of the first galaxies. In the early universe, shortly after the Big Bang, matter was spread out almost uniformly. There were tiny fluctuations, small differences in density, but overall, the universe was a smooth, hot plasma. As the universe expanded and cooled, these tiny fluctuations began to grow. Gravity pulled matter together. Denser regions became even denser, and over time, structure began to form. But this process would have been too slow if only normal matter were involved. Normal matter was still interacting strongly with radiation. Photons pushed it around, preventing it from clumping together quickly. Dark matter, however, was unaffected by radiation. It did not interact with photons, so it could begin clumping together much earlier. Dark matter formed the first gravitational wells, the first seeds of structure, and normal matter fell into these wells, cooling and condensing, forming the first stars and galaxies. Without dark matter, galaxies would have taken much longer to form, perhaps so long that the universe would look very different today. Dark matter accelerated the process. It provided the scaffolding, the framework, upon which all visible structure was built. In this sense, dark matter is not just a passive component of the universe. It is an active participant, a sculptor of cosmic history, shaping the evolution of the universe from its earliest moments, allowing galaxies to form, stars to ignite, planets to coalesce, and life to emerge. Dark matter influences the large-scale structure of the universe. On the grandest scales, dark matter shapes the distribution of galaxies across the cosmos. Simulations show that dark matter forms vast filaments, sheets, and walls of matter stretching across hundreds of millions of light-years. These structures are too large to see in a single glance, but they reveal themselves in surveys that map millions of galaxies. The pattern is unmistakable. Galaxies cluster along filaments. They gather at the intersections where filaments meet, and they avoid the vast voids between the filaments. This pattern is the cosmic web, and it is shaped almost entirely by dark matter. Normal matter simply follows the gravitational roads laid down by dark matter, flowing along the filaments like rivers following valleys. The cosmic web is one of the most breathtaking structures in the universe. Imagine a vast network of highways stretching across space. Each highway is a filament of dark matter, and along these highways, galaxies travel and gather. At the intersections, massive galaxy clusters form. In between, the voids remain almost empty. This architecture defines the universe on its largest scales, and it is all held together by the invisible presence of dark matter. The cosmic microwave background reveals clues about dark matter. One of the most important sources of information about dark matter comes from the cosmic microwave background, or CMB. This is the faint glow of radiation that fills the entire universe. It is the afterglow of the Big Bang, light that has been traveling through space for nearly 14 billion years. When we observe the CMB, we see tiny fluctuations in temperature. Some regions are slightly warmer, others are slightly cooler. These fluctuations are incredibly important. They tell us about the distribution of matter in the early universe, and they provide strong evidence for dark matter. The pattern of fluctuations matches exactly what we would expect if most of the matter in the universe were dark. Normal matter alone could not produce the observed pattern. But when we include dark matter in our models, the predictions match the observations beautifully. The CMB also tells us how much dark matter there is. By measuring the size and amplitude of the temperature fluctuations, scientists can calculate the density of dark matter in the universe. The answer they get is consistent with all other measurements. Dark matter makes up about 85% of the total matter. This consistency across different methods gives us confidence that dark matter is real. Dark matter and dark energy are not the same thing. It is easy to confuse dark matter with dark energy, especially since both have the word dark in their names. But they are completely different phenomena. Dark matter is a form of matter. It has mass. It exerts gravitational pull. It clumps together to form structure. Dark energy, on the other hand, is not matter at all. It is a property of space itself. It does not clump. It is spread uniformly throughout the universe. And instead of pulling things together, it pushes them apart. Dark energy is responsible for the accelerating expansion of the universe. Observations show that the expansion of the universe is speeding up over time. This acceleration is driven by dark energy. Dark matter, by contrast, slows down the expansion. Its gravity tries to pull everything back together. The universe we live in is shaped by a cosmic tug-of-war between dark matter, which tries to collapse structures, and dark energy, which tries to push everything apart. Together, dark matter and dark energy make up about 95% of the universe. Dark energy accounts for about 68%. Dark matter, about 27%. And normal matter, the stuff we are made of, the stars and planets and gas, makes up only about 5%. We live in a universe where the familiar is the rare exception, and the mysterious is the overwhelming rule. Dark matter may have its own complex physics. Most discussions of dark matter treat it as a single substance, but it is possible that dark matter is more complicated than we think. Just as normal matter comes in many forms, atoms, molecules, solids, liquids, gases, dark matter might also have a rich internal structure. There could be multiple types of dark matter particles. They might interact with each other in ways we do not yet understand. They might even form dark atoms or dark molecules. Some scientists have proposed the idea of self-interacting dark matter. This is dark matter that does interact with itself, not through electromagnetism, but through some other force unique to the dark sector. If this is true, dark matter might behave differently on different scales. It might clump more tightly in some regions and less tightly in others. This could help explain some puzzles that current models of dark matter struggle with. The idea that dark matter has its own hidden physics is speculative, but it is a reminder that we are still in the early stages of understanding this mysterious substance. We know it is there, We know it shapes the universe, but we do not yet know what it truly is. The universe may have secrets within secrets, layers of reality we have not yet begun to explore. Our Milky Way galaxy is surrounded by a halo of dark matter. Our home galaxy, the Milky Way, is no exception to the rule. Like all galaxies, it is embedded in a vast halo of dark matter. This halo extends far beyond the visible disk of stars. It reaches out, perhaps 200,000 light-years from the galactic center, maybe even farther. The mass of this halo is immense, far greater than all the stars in the galaxy combined. As the Sun orbits the center of the Milky Way, it is held in its path by the gravity of this dark matter halo. The same is true for every other star in the galaxy. Without the halo, the stars would drift away. The galaxy would dissolve. But the dark matter holds it together, like an invisible scaffold supporting a glowing structure. We are, in a very real sense, living inside dark matter. As the Earth orbits the Sun and the Sun orbits the galaxy, we are constantly moving through this dark matter halo. Dark matter particles are passing through us, through the Earth, through everything, all the time. We do not feel them, we do not see them, but they are there, silent travelers from the hidden universe. Dark matter might be streaming through you right now. At this very moment, countless dark matter particles are likely passing through your body. They come from the halo surrounding the Milky Way. They move at high speeds, hundreds of kilometers per second. But because they do not interact with normal matter, they pass right through the walls of your home, through the Earth, through you, without leaving a trace. It is a strange and humbling thought. We are surrounded by, immersed in, an ocean of invisible particles. They have mass, they have motion, but they are completely undetectable to our senses. We live our lives unaware of this hidden flow, this dark river coursing through the universe and through us. Scientists estimate that billions of dark matter particles pass through your body every second, yet not a single one will interact with your atoms in a way you could feel. They are ghosts in the truest sense. Present but intangible, real but unseen. A reminder that reality extends far beyond what we can perceive. The search for dark matter has driven technological innovation. The quest to detect dark matter has pushed scientists to develop some of the most sensitive instruments ever built: deep underground detectors, cryogenic systems that cool materials to a fraction of a degree above absolute zero, shielding to block out every possible source of interference. These technologies were created for the sole purpose of catching a glimpse of the invisible. But the innovations developed for dark matter research have found applications far beyond particle physics. The same techniques used to build sensitive dark matter detectors are now used in medical imaging, in materials science, in quantum computing. The search for dark matter has expanded our technological capabilities in unexpected ways. This is often how science works. The pursuit of fundamental knowledge, even when it seems abstract or distant from everyday life, leads to practical advances. We build new tools, we develop new methods, and those tools and methods find uses we never anticipated. The search for dark matter is not just about understanding the universe. It is also about expanding the boundaries of what we can do. Dark matter might solve mysteries we have not yet discovered. One of the most exciting possibilities is that dark matter might help us understand other puzzles in physics. There are many phenomena in the universe that we do not fully understand. Strange signals from space, anomalies in particle physics, unexplained patterns in the cosmic microwave background. Some of these might be connected to dark matter. For example, there have been hints of excess gamma rays coming from the center of the Milky Way. Some scientists think these could be produced by dark matter particles colliding and annihilating each other. If true, this would be indirect evidence of dark matter interactions. Other researchers are looking at unusual signals in cosmic rays, high-energy particles from space, to see if dark matter might be involved. None of these hints have been confirmed yet. They remain tantalizing possibilities. But they remind us that the discovery of dark matter might open doors to entirely new physics. It might help us solve problems we did not even know were related. The universe is deeply interconnected, and dark matter, as the dominant form of matter, is likely woven into many aspects of cosmic history and structure that we have yet to unravel. Dark matter halos can merge when galaxies collide. When two galaxies collide, a process that unfolds over hundreds of millions of years, their dark matter halos merge as well. The visible galaxies, the stars and gas, interact in dramatic ways. Stars are flung into new orbits. Gas clouds collide and form new stars. But the dark matter behaves differently. Because it does not interact with itself or with normal matter, it simply passes through. As the two galaxies spiral around each other, pulled together by gravity, their dark matter halos blend. The result is a single, larger halo surrounding the merged galaxy. This process has happened countless times throughout cosmic history. In fact, our own Milky Way is on a collision course with the Andromeda Galaxy. In about 4 billion years, the two will merge. And when they do, their dark matter halos will merge as well, creating a new, even larger halo around the combined galaxy. These mergers are an important part of how structure grows in the universe. Galaxies grow by merging with other galaxies, and their dark matter halos grow the same way. The universe is a dynamic place, constantly reshaping itself through the pull of gravity, and dark matter is at the heart of this process. Dwarf galaxies are dominated by dark matter. While large galaxies like the Milky Way have a lot of dark matter, they also have a lot of stars and gas. But smaller galaxies, called dwarf galaxies, are even more dominated by dark matter. In some dwarf galaxies, dark matter can make up 99% or more of the total mass. The visible stars are just a tiny speck in a vast dark matter halo. This makes dwarf galaxies especially interesting for studying dark matter. Because there is so little normal matter, the effects of dark matter are more pronounced. Scientists study how stars move in dwarf galaxies, how the galaxies orbit larger galaxies like the Milky Way, and how they respond to gravitational forces. All of these observations provide clues about the nature of dark matter. Some dwarf galaxies orbit the Milky Way like satellites. There are dozens of them, small collections of stars held together by gravity, orbiting our galaxy. By studying their motions, scientists can map the distribution of dark matter in the Milky Way's halo. These tiny galaxies are like tracers, revealing the invisible structure that surrounds us. Dark matter might have played a role in the formation of supermassive black holes. At the center of most large galaxies, including the Milky Way, there is a supermassive black hole. These black holes have masses millions or even billions of times greater than the Sun. How they formed is still a mystery. They appear to have existed very early in the universe, not long after the first galaxies formed. This is puzzling because it is not clear how they could have grown so large so quickly. One possibility is that dark matter helped them form. In the early universe, dark matter clumped together first, creating dense regions where gravity was very strong. Normal matter fell into these regions and began to collapse. If enough matter collapsed quickly enough, it could have formed the seeds of supermassive black holes. Dark matter would have provided the gravitational environment needed for this to happen. This is still speculative, but it is an example of how dark matter might have influenced the evolution of the universe in ways we are only beginning to understand. The formation of galaxies, of stars, of black holes, all of these processes were shaped by the presence of dark matter. It is the hidden sculptor, working behind the scenes, guiding the development of cosmic structure. The distribution of dark matter is not perfectly smooth. While dark matter forms large halos and filaments, it is not distributed perfectly evenly. Computer simulations show that dark matter halos have substructure, smaller clumps of dark matter within the larger halo. These are sometimes called subhalos. They are the remnants of smaller halos that were absorbed as the larger halo grew. Our own Milky Way halo is thought to contain thousands or even millions of these subhalos. Most of them are invisible because they do not contain any stars. They are pure dark matter, but their gravitational effects can still be detected. They tug on nearby stars and gas. They create small distortions in the orbits of objects in the galaxy. Detecting these subhalos is difficult, but it is important because they provide a test of our theories about dark matter. Different models of dark matter predict different amounts of substructure. By observing how many subhalos exist and how they are distributed, scientists can narrow down what dark matter might be. Dark matter does not collapse into black holes the way normal matter does. You might wonder, if dark matter has mass and gravity, why does it not collapse into black holes? The answer has to do with how dark matter behaves. Normal matter can lose energy by emitting radiation. When gas clouds collapse, they heat up and radiate that heat away. This allows them to cool and collapse further, eventually forming dense objects like stars or black holes. Dark matter cannot do this. It does not interact with radiation. So when dark matter particles move past each other, they do not lose energy. They cannot cool. They cannot collapse into tight, dense objects. Instead, dark matter remains spread out in large, diffuse halos. This is why dark matter does not form stars or black holes. It simply does not have the physics to do so. This difference is crucial. It means that dark matter and normal matter play different roles in the universe. Normal matter forms the visible structures we see: stars, planets, galaxies. Dark matter forms the invisible scaffolding that holds those structures together. Both are necessary. Without normal matter, there would be no stars or life. Without dark matter, there would be no galaxies or cosmic web. The universe requires both to function. Some scientists are looking for dark matter using particle accelerators. While most dark matter searches look for particles from space, some scientists are trying to create dark matter in the lab. Particle accelerators, like the Large Hadron Collider in Europe, smash particles together at incredibly high energies. These collisions can create new particles that do not normally exist in nature. If dark matter particles can be created this way, they would immediately escape the detector. Because they do not interact with normal matter, they would be invisible. But scientists can still detect them indirectly. By measuring the energy of all the other particles produced in the collision, they can see if some energy is missing. That missing energy would be a sign that dark matter particles were created and escaped. So far, no such signal has been found, but the search continues. Every collision, every experiment provides new data. It helps scientists rule out certain possibilities and refine their theories. The search for dark matter is a patient, methodical process. It requires persistence and creativity, and it represents one of the great scientific quests of our time. Dark matter might interact through a fifth fundamental force. We know of 4 fundamental forces in nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These forces govern how particles interact with each other. Normal matter interacts through all 4, But dark matter seems to interact only through gravity. It does not respond to electromagnetism or the strong force. It might interact weakly through the weak force, which is why WIMPs are a popular candidate, but even that is uncertain. Some physicists have speculated that dark matter might interact through a fifth force, a force that only affects dark matter. This force would be completely separate from the forces we know. It would exist in what is sometimes called the dark sector, a hidden realm of particles and interactions that we cannot directly observe. If such a force exists, it could have profound implications. It would mean that dark matter has its own rich physics, its own interactions and dynamics. It might even mean that dark matter can clump in different ways, form dark structures, or evolve in ways we have not yet imagined. This is speculative, but it is a reminder that we are still at the beginning of understanding dark matter. There is much we do not know, and the truth might be stranger and more interesting than we expect. Dark matter affects the motion of satellite galaxies. Around the Milky Way, there are dozens of smaller galaxies that orbit like satellites. These dwarf galaxies are held in their orbits by the gravity of the Milky Way's dark matter halo. By studying how these satellites move, scientists can learn about the distribution and properties of dark matter. One interesting puzzle is that computer simulations predict more satellite galaxies than we actually observe. This is called the missing satellites problem. Simulations based on current dark matter models suggest there should be hundreds of small dark matter halos around the Milky Way. But we only see a few dozen galaxies. Where are the rest? There are several possible explanations. Maybe many of the predicted halos do not contain stars, so we cannot see them. Maybe the process of galaxy formation is more complicated than we thought, and not every dark matter halo gets a galaxy. Or maybe our models of dark matter are missing something. This puzzle is still being investigated, but it highlights how observations of satellite galaxies can teach us about dark matter. Dark matter might be made of sterile neutrinos. Another candidate for dark matter is a particle called the sterile neutrino. Normal neutrinos are tiny, nearly massless particles that barely interact with anything. They are produced in nuclear reactions, like those in the sun, and billions of them pass through your body every second without you noticing. Sterile neutrinos would be similar, but even more elusive. They would not interact through the weak force like normal neutrinos. They would interact only through gravity. If sterile neutrinos exist and have a small amount of mass, they could account for dark matter. They would have been produced in the early universe and would now fill space, forming the halos and filaments we observe. Some experiments are searching for sterile neutrinos by looking for tiny signals in the decay of radioactive materials or in the cosmic microwave background. The idea of sterile neutrinos is appealing because it connects dark matter to neutrino physics, a field we already know something about. It suggests that dark matter might not be completely foreign to the physics we understand, but like other candidates, sterile neutrinos have not yet been detected. The search continues. Gravitational lensing reveals the invisible shape of dark matter. One of the most powerful tools for mapping dark matter is gravitational lensing. When light from a distant galaxy passes near a massive object, the gravity of that object bends the light's path. This is a prediction of Einstein's theory of general relativity. The bending of light can create multiple images of the distant galaxy, or it can stretch and distort the galaxy's shape. By studying these distortions, astronomers can create maps of where the mass is, even if that mass is invisible. They can trace the distribution of dark matter in galaxy clusters, in individual galaxies, and along the cosmic web. These maps reveal that dark matter is not uniformly distributed. It clumps in some places and is sparse in others. It forms filaments and halos, just as simulations predict. Gravitational lensing has provided some of the clearest images of dark matter's influence. It has shown us where dark matter is, how much of it there is, and how it shapes the paths of light across the universe. It is like drawing a map of the wind by watching how it moves the leaves. We cannot see the wind itself, but we can see its effects. And from those effects, we can infer its presence and its structure. Dark matter could help explain the motion of stars in elliptical galaxies. Elliptical galaxies are different from spiral galaxies, like the Milky Way. They do not have the flat, rotating disk of stars. Instead, they are more spherical or ellipsoidal, and their stars move in random orbits rather than in a coordinated rotation. Despite these differences, elliptical galaxies also show evidence of dark matter. By measuring the speeds and orbits of stars in elliptical galaxies, astronomers can calculate how much mass is present. Once again, they find more mass than can be accounted for by visible stars and gas. That extra mass is dark matter. In fact, elliptical galaxies seem to have even more dark matter, proportionally, than spiral galaxies. Their dark matter halos are larger and more massive. This consistency across different types of galaxies is important. It tells us that dark matter is a universal feature of galaxies, not something unique to one kind. Whether a galaxy is spiral or elliptical, large or small, young or old, it is embedded in dark matter. This universality strengthens the case that dark matter is real and fundamental to the structure of the universe. The temperature of galaxy clusters depends on dark matter. When astronomers observe galaxy clusters with X-ray telescopes, they can measure the temperature of the hot gas filling the space between galaxies. This gas is incredibly hot, millions of degrees. The temperature tells us about the gravitational potential well of the cluster. The deeper the well, the more gravity is pulling the gas inward, and the hotter the gas becomes. By measuring the temperature, scientists can calculate how much mass is present in the cluster. And once again, the answer is far more than the visible galaxies alone. The extra mass is dark matter. This method provides an independent confirmation of dark matter's existence. It uses completely different physics, X-ray observations, instead of optical or gravitational lensing, yet arrives at the same conclusion. Dark matter is there, shaping the cluster, holding it together. This convergence of evidence from multiple methods is one of the reasons scientists are confident that dark matter is real. It is not just one observation or one technique. It is many observations, using many techniques, all pointing to the same unseen presence. Dark matter affects how galaxies form stars. The process of star formation is influenced by dark matter in subtle ways. Stars form when clouds of gas collapse under their own gravity. But for this to happen, the gas needs to be concentrated in certain regions. Dark matter helps create those regions. Its gravity pulls gas into the centers of dark matter halos, where it can cool, condense, and eventually form stars. Without dark matter, the process would be much slower and less efficient. The gas would be more spread out. It would take longer to collect enough material to form stars. Galaxies would be smaller and dimmer. The universe would look very different. Dark matter also affects how stars are distributed within a galaxy. The shape and size of the dark matter halo influence where gas accumulates and where stars form. In this way, dark matter is not just a passive backdrop. It actively shapes the visible structures we see. It determines where galaxies form, how large they grow, and how many stars they contain. The edges of dark matter halos are difficult to define. Unlike a planet or a star, which has a clear surface, a dark matter halo does not have sharp edges. It gradually fades out as you move farther from the center. The density of dark matter decreases slowly with distance, but it never quite reaches zero. In principle, The halo extends indefinitely, though at some point it becomes so diffuse that it is negligible. This makes it difficult to say exactly where a dark matter halo ends. Scientists often define the edge of a halo as the radius within which the average density is a certain multiple of the cosmic average. This is an arbitrary definition, but it provides a useful way to talk about the size of halos and compare them to one another. In reality, dark matter halos blend into each other. The halo of one galaxy overlaps with the halo of its neighbor. On the largest scales, everything is connected by the cosmic web. There are no clear boundaries, just gradients of density, rising and falling across the vastness of space. Dark matter might have influenced the formation of the first stars. The very first stars in the universe, formed a few 100 million years after the Big Bang, are thought to have been very different from stars today. They were much larger, much hotter, and much more short-lived. These primordial stars formed in the densest regions of the early universe, regions where dark matter had already begun to clump together. Dark matter provided the gravitational wells into which hydrogen and helium gas collapsed. Without dark matter, these wells would not have formed so quickly or so deeply. The first stars might have been delayed, or they might have been smaller and less luminous. Dark matter set the stage for the birth of the first light in the universe. These first stars played a crucial role in cosmic history. They produced the first heavy elements, which were scattered into space when the stars exploded as supernovae. Those elements eventually became part of later generations of stars and planets. In this way, dark matter indirectly contributed to the chemical evolution of the universe. It shaped not just the structure of the cosmos, but the very building blocks from which planets and life are made. The nature of dark matter remains one of the greatest unsolved problems in physics. Despite decades of research, we still do not know what dark matter is. We have strong evidence that it exists. We know it shapes galaxies and the large-scale structure of the universe. We can map its distribution through gravitational lensing and other methods, but we do not know what particles or entities it is made of. This is both frustrating and exciting. Frustrating because we have been searching for so long without a definitive answer. Exciting because it means there is still so much to discover. The solution to the dark matter puzzle could lead to a revolution in physics. It might require new particles, new forces, new theories that extend or replace our current understanding. Science thrives on mysteries. They drive innovation. They inspire new experiments. They challenge us to think more deeply and creatively. Dark matter is one of the great mysteries of our time, and solving it will be one of the great achievements. We may be on the verge of a breakthrough, or it may take many more years, but the search continues, guided by curiosity and the desire to understand the universe more fully. Every galaxy we observe is an island of light in an ocean of dark matter. When you look at images of galaxies, you see beautiful spirals or elliptical glows, bright cores and sweeping arms. But what you are seeing is only the visible matter, the stars and gas. Surrounding each of these luminous islands is a vast, invisible ocean, a halo of dark matter that dwarfs the visible galaxy in size and mass. The galaxy is the lighthouse. The dark matter is the sea around it. This perspective changes how we think about galaxies. They are not isolated objects floating in empty space. They are deeply embedded in a structure we cannot see. The dark matter is not just around them. It is part of them. It defines their size, their shape, their motion. Without it, they would not be what they are. The visible galaxy is the surface manifestation of a much larger, hidden entity. We live on a small planet orbiting a typical star in one of these islands of light. But we are surrounded by, immersed in, the dark ocean. It is the unseen reality that makes our visible reality possible. Dark matter's gravity can bend space and time. According to Einstein's theory of general relativity, mass and energy curve the fabric of space-time. The more mass, the stronger the curvature. And dark matter, having mass, curves space-time just like normal matter does. In fact, because there is so much dark matter, it contributes significantly to the curvature of space-time on large scales. This curvature affects how light travels through the universe. It affects how galaxies move. It even affects the passage of time. Near a massive concentration of dark matter, time runs slightly slower than it does in less dense regions. This effect is incredibly small. You would never notice it in everyday life, but it is real. And it is part of how the universe works. The bending of space-time by dark matter is one of the ways we detect it. Gravitational lensing, the bending of light around massive objects, is a direct consequence of this curvature. By studying how light is bent, we can map the invisible landscape of dark matter. We can see the hills and valleys in space-time created by its mass. In this way, dark matter reveals itself not through light, but through the geometry of the universe. Scientists use supercomputers to simulate how dark matter shapes the universe. Understanding how the universe evolved requires more than just observations. It requires simulations. Scientists use powerful supercomputers to model the behavior of dark matter and normal matter over billions of years. They start with the conditions shortly after the Big Bang, a nearly uniform soup of particles. Then they let the simulation run forward, applying the laws of gravity and physics. In these simulations, dark matter clumps together first. It forms halos and filaments. Normal matter falls into these structures, forming galaxies and stars. Over time, galaxies merge. Clusters form. The cosmic web emerges. The simulations can track billions of particles, each representing a chunk of dark matter or normal matter, and they can span the entire observable universe. The results are stunning. When scientists compare the simulations to real observations, they match the distribution of galaxies, the structure of the cosmic web, the properties of galaxy clusters. All of these agree with what the simulations predict. This is powerful evidence that our understanding of dark matter is on the right track. The simulations are like virtual universes, and they show that dark matter is essential to making a universe that looks like ours. The amount of dark matter in the universe is precisely measured. One of the remarkable achievements of modern cosmology is the precision with which we have measured the composition of the universe. Through observations of the cosmic microwave background, the distribution of galaxies, the behavior of supernovae, and other methods, scientists have determined that about 27% of the universe is dark matter. This might not sound precise, but in fact, we know this number to within a few percent. We know that dark matter is not 10% or 50%. It is about 27%. This precision comes from the convergence of many different observations. Each method provides an independent measurement, and they all agree. This agreement gives us confidence that the number is correct. The rest of the universe is dark energy, about 68%, and normal matter, about 5%. These proportions define the universe we live in. If dark matter were more or less abundant, the universe would be very different. Galaxies might not form, or they might form too quickly. The fact that we live in a universe with just the right amount of dark matter is one of the many fine-tunings that make our existence possible. Dark matter helps explain the observed abundance of elements in the universe. In the early universe, shortly after the Big Bang, the first atomic nuclei were formed. This process is called Big Bang nucleosynthesis. The abundance of light elements, hydrogen, helium, and a tiny amount of lithium and other elements was determined by the conditions during this period. The density of normal matter, the temperature, and the expansion rate all played a role. By measuring the abundances of these elements today, scientists can infer the density of normal matter in the early universe. The answer they get is about 5% of the total mass energy of the universe. This is consistent with all other measurements of normal matter. But it also tells us that most of the matter must be something else, something that was present in the early universe but did not participate in nucleosynthesis. That something is dark matter. Dark matter does not form atomic nuclei. It does not interact with the processes that create hydrogen and helium, so it does not affect the abundance of light elements. But it does affect the overall dynamics of the universe. Its gravity influences the expansion rate and the formation of structure. The consistency between nucleosynthesis predictions and observations is another piece of evidence that dark matter is real. Dark matter might explain certain anomalies in the motion of stars. Astronomers have noticed a few puzzling anomalies in the motion of stars and other objects. One example is the orbit of stars at the very edge of the Milky Way. Some of these stars move in unexpected ways. Their orbits suggest there might be additional mass somewhere, pulling on them. That mass could be dark matter substructure, small clumps of dark matter within the Milky Way's halo. Another example involves hypervelocity stars. These are stars moving so fast that they will eventually escape the galaxy. Some of them seem to have been flung out by interactions with massive objects. Those objects might be dark matter clumps, or they might be black holes. It is not yet clear, but dark matter is one possible explanation. These anomalies are not conclusive evidence on their own. There could be other explanations, but they add to the growing body of hints that dark matter has structure and complexity, that it is not just a smooth, featureless halo, but something more dynamic and interesting. The search for dark matter involves collaborations across the globe. The quest to understand dark matter is a global effort. Scientists from dozens of countries work together, sharing data, building experiments, developing theories. Detectors are buried deep underground in mines on several continents. Particle accelerators in Europe and Asia search for signs of dark matter. Telescopes around the world and in space map its distribution. This collaboration is essential. No single country or institution could solve the dark matter puzzle alone. It requires expertise in particle physics, astrophysics, cosmology, engineering, and more. It requires resources and infrastructure on a massive scale. And it requires a shared commitment to understanding the universe. Science, at its best, transcends borders. It brings people together in pursuit of common goals. The search for dark matter is a testament to what humanity can achieve when we work together. It is a reminder that the universe belongs to all of us, and the answers we seek are worth the effort. Dark matter does not produce or interact with magnetic fields. Magnetic fields are generated by moving electric charges. They play a crucial role in the behavior of normal matter. In space, magnetic fields thread through gas clouds, influence the motion of charged particles, and help drive processes like star formation. But dark matter does not have electric charge, so it does not generate magnetic fields, and it does not respond to them. This is another way in which dark matter is fundamentally different from the matter we know. It is invisible to electromagnetic forces. It does not emit light. It does not respond to magnets. It is immune to the forces that shape so much of the visible universe. And yet, it is not immune to gravity. Gravity is the one force that governs its behavior, and through gravity, it shapes everything else. This simplicity is both a blessing and a curse. It makes dark matter easier to model. We do not have to worry about magnetic fields or radiation pressure. or other complex electromagnetic effects. But it also makes dark matter harder to detect. Without electromagnetic interactions, we have fewer ways to study it. We must rely on gravity alone. And gravity is a gentle, subtle force, difficult to measure with precision. Dark matter may hold clues to physics beyond the Standard Model. The Standard Model of particle physics is our best description of the fundamental particles and forces. It has been incredibly successful. It explains almost everything we can observe in particle physics experiments. But it has limitations. It does not include gravity. It does not explain dark matter. And it does not explain several other puzzles, like why neutrinos have mass, or why there is more matter than antimatter in the universe. Many physicists believe that the Standard Model is not the final word, that there is a deeper, more complete theory waiting to be discovered, and dark matter might be the key. If dark matter is made of particles beyond the Standard Model, discovering those particles could open the door to new physics. It could reveal new forces, new symmetries, new principles. This is one reason the search for dark matter is so important. It is not just about understanding one mysterious substance. It is about understanding the fundamental nature of reality, about discovering the rules that govern the universe at its deepest level. Dark matter might be the thread that, when pulled, unravels a whole new tapestry of knowledge. The cosmic web is a testament to the power of gravity. Gravity is the weakest of the four fundamental forces. On small scales, it is almost negligible. But on large scales, gravity dominates. It shapes the motion of planets, stars, galaxies, and clusters. It carved the cosmic web from the near-uniform distribution of matter in the early universe, and it is driven, primarily, by dark matter. The cosmic web is a beautiful illustration of how a simple force, acting over vast distances and timescales, can create intricate structure. The filaments and voids, the clusters and superclusters, all of this emerged from the pull of gravity. There was no blueprint, no design, just particles pulling on each other over billions of years, guided by the laws of physics. Dark matter was the amplifier. It made gravity stronger. It allowed structure to form faster and more efficiently. Without it, the universe would be a much less interesting place. A sparse, dim expanse of isolated stars. With dark matter, we have galaxies and clusters, and the majestic web that connects them all. Gravity, amplified by dark matter, is the sculptor of the cosmos. Dark matter's influence extends to the smallest dwarf galaxies. Even the tiniest galaxies, dwarf galaxies with only a few thousand stars, show the influence of dark matter. These galaxies are so small that they are barely visible. Yet their stars move faster than the visible mass alone can explain. This tells us that even these tiny systems are embedded in dark matter halos. In some ultra-faint dwarf galaxies, the ratio of dark matter to normal matter is astonishing. More than 1,000 to 1, these galaxies are almost entirely dark matter. The stars are just a faint glow in a vast invisible sea. Studying these galaxies helps scientists understand how dark matter behaves on the smallest scales, and it tests our theories of galaxy formation. The fact that dark matter shapes galaxies across such a huge range of sizes, from the tiniest dwarfs to the largest giants, is powerful evidence of its universality. It is not a quirk of one type of galaxy or one region of space. It is a fundamental feature of the universe. Dark matter particles might have lifetimes longer than the age of the universe. If dark matter is made of particles, those particles are likely very stable. They do not decay, or at least they decay so slowly that most of them are still around today, nearly 14 billion years after the Big Bang. This stability is important. If dark matter particles decayed quickly, they would have vanished long ago, and we would not see their effects today. Some theories predict that dark matter particles can decay, but only on timescales much longer than the age of the universe, trillions of years, or even longer. If this is true, then dark matter is essentially eternal on cosmic timescales. It was created in the early universe, and it will persist far into the future, long after the stars have burned out and the galaxies have faded. This stability is part of what makes dark matter such a dominant component of the universe. It does not go away. It does not change. It is a permanent presence, shaping the universe from beginning to end. Dark matter helps us measure the expansion rate of the universe. The rate at which the universe is expanding, known as the Hubble constant, is one of the most important numbers in cosmology. It tells us how fast galaxies are moving apart, and it helps us determine the age and fate of the universe. Measuring the Hubble constant requires understanding the distribution of matter, both normal and dark. Dark matter affects the dynamics of galaxy clusters and the large-scale structure of the universe. By studying these effects, scientists can infer the expansion rate. Different methods give slightly different values, and there is currently a small tension between measurements. But dark matter is a key part of all these methods. Without accounting for it, we could not accurately measure the expansion of the universe. This highlights how interconnected our understanding of the universe is. Dark matter, the expansion rate, the formation of structure, the cosmic microwave background, all of these are linked. Solving one puzzle often requires solving others, and dark matter is at the heart of many of these puzzles. Dark matter does not form planets or moons. We might wonder, if dark matter has mass, could it clump together to form objects like planets or moons? The answer is no, for several reasons. First, dark matter does not interact with itself in a way that allows it to lose energy and collapse into tight, bound objects. Second, even if it could collapse, it would not emit light or heat, so we would never see it. And third, dark matter does not interact with normal matter, so it could not form the rocky or gaseous structures we associate with planets. Dark matter remains diffuse. It forms halos and filaments, but not compact objects. It is a background presence, not a foreground feature. This is part of why it took so long to discover. It does not make itself obvious. It does not shine. It does not form discrete, identifiable objects. It is everywhere and nowhere, a hidden layer of reality. This also means that there are no dark matter planets or dark matter life, at least not in any form we can imagine. Life, as we know it, requires complex chemistry. And chemistry requires electromagnetic interactions between atoms. Dark matter does not do chemistry. It is, in a sense, inert. It shapes the universe, but it does not participate in the rich, complex processes that give rise to stars and planets and life. The density of dark matter in our solar system is incredibly low. While the Milky Way's dark matter halo extends far beyond the visible stars, the density of dark matter at our location in the solar system is very low. Estimates suggest there is less than 1/1000th of a gram of dark matter per cubic centimeter of space. That is incredibly sparse, far thinner than the best vacuum we can create on Earth. This means that even though dark matter particles are passing through us all the time, there are not that many of them in any given volume. And because they do not interact with normal matter, we do not notice them. They have no effect on our daily lives. They do not affect the motion of planets or spacecraft. Their presence is negligible on the scale of the solar system. It is only on much larger scales, the scale of galaxies and clusters, that dark matter's gravity becomes significant. That is where its mass adds up. That is where it shapes structure and holds things together. In our corner of the universe, dark matter is a faint whisper, but across the cosmos, it is a defining presence. dark matter might interact with neutrinos in ways we do not yet understand. Neutrinos are among the most mysterious particles in the Standard Model. They are incredibly light, nearly massless. They interact only through the weak nuclear force and gravity. Billions of neutrinos from the Sun pass through your body every second, and you never feel them. In some ways, neutrinos are similar to dark matter. Elusive, hard to detect, weakly interacting. Some theories propose that dark matter and neutrinos might interact with each other, not through the forces we know, but through some new force or mechanism. If this is true, studying neutrinos could give us clues about dark matter, and studying dark matter could teach us about neutrinos. The two mysteries might be connected. This is speculative, but it is an example of how scientists look for connections between different puzzles. The universe is not a collection of isolated problems. It is a single, interconnected system, and solving one part often sheds light on others. Dark matter existed long before stars and galaxies. In the very early universe, in the first moments after the Big Bang, the universe was a hot, dense plasma. Particles were constantly being created and annihilated. As the universe expanded and cooled, this process slowed down. Eventually, dark matter particles froze out. They stopped being created and destroyed, and their population became fixed. This happened very early, perhaps when the universe was less than a second old. From that moment on, dark matter has been a permanent presence. It was there long before the first stars formed. Long before the first galaxies, it shaped the conditions in which those structures would later emerge. In a sense, dark matter is older than light, older than the stars. It is a relic from the earliest moments of cosmic history. When we study dark matter, we are studying the primordial universe. We are looking back to a time when the cosmos was young and simple, before complexity and structure emerged. Dark matter is a witness to that ancient past, and by understanding it, we can learn about the birth of the universe itself. The distribution of dark matter determines where galaxies form. In the early universe, tiny fluctuations in the density of dark matter created regions that were slightly denser than average. These regions had a little more gravity, so they pulled in more matter. Over time, these dense regions grew denser. They became the seeds of galaxies. Normal matter fell into these seeds, cooled, and formed stars. The largest fluctuations became the centers of galaxy clusters. Smaller fluctuations became individual galaxies. The cosmic web emerged from the pattern of these fluctuations. This process is called hierarchical structure formation. Small structures form first, then they merge to create larger structures. And dark matter drove the whole process. Without dark matter, these fluctuations would not have grown fast enough. The universe would have remained smooth and featureless for much longer. By the time structure began to form, the expansion of the universe would have spread matter too thin. Galaxies as we know them might never have formed. Dark matter was the catalyst that allowed the universe to transition from smooth plasma to the rich, structured cosmos we see today. Dark matter is essential to the existence of life. This might seem like a strange claim. How could something invisible and intangible be essential to life? But consider the chain of causation. Life requires planets. Planets require stars. Stars require galaxies. And galaxies require dark matter. Without dark matter, galaxies would not have formed. Or they would have formed much later and been much smaller. Stars might be rare and isolated. Planets might be even rarer. The Earth exists because the Milky Way exists, and the Milky Way exists because of dark matter. In this sense, We owe our existence to the invisible scaffolding that holds the universe together. Dark matter shaped the environment in which stars could form, in which heavy elements could be created, in which planets like Earth could coalesce, and in which life could emerge. This is a humbling thought. The atoms in our bodies were forged in stars, and those stars exist because of dark matter. We are part of a cosmic story that stretches back to the earliest moments of the universe. And dark matter is a key character in that story. Dark matter's effects are seen in the redshifts of distant galaxies. When astronomers observe distant galaxies, they measure how much the light from those galaxies has been shifted toward the red end of the spectrum. This redshift is caused by the expansion of the universe. The farther away a galaxy is, the faster it is moving away from us, and the greater its redshift. But the expansion rate is not constant everywhere. It is affected by the distribution of matter, including dark matter. Regions with more matter have stronger gravity, which slightly slows the expansion. By carefully measuring the redshifts of many galaxies and comparing them to predictions, scientists can infer how matter, both normal and dark, is distributed. These measurements agree with what we expect if dark matter is real. They provide another independent confirmation. Every method we use to study the universe points to the same conclusion. Dark matter is there. It shapes the expansion. It influences the motion of galaxies. It is a fundamental part of the cosmic landscape. Dark matter halos might contain ancient, wandering black holes. In the early universe, some of the very first stars were massive. When they died, they might have left behind black holes. Over billions of years, some of these black holes might have been ejected from their host galaxies through gravitational interactions. They would wander through the dark matter halos, invisible and alone. These wandering black holes would be incredibly difficult to detect. They do not emit light unless they are actively feeding on gas, which most of them are not. But they do have mass, and their presence in dark matter halos could affect the motion of stars and gas in subtle ways. Some scientists are looking for these effects, hoping to find evidence of wandering black holes hiding in the dark. If such black holes exist, they would be another hidden component of the universe, another piece of the puzzle. They would remind us that the cosmos is full of things we have not yet discovered, things that exist in the shadows, waiting to be found. Dark matter remains stable over cosmic time. Unlike stars, which burn and fade, or gas clouds, which condense and disperse, dark matter is essentially unchanging. It does not evolve. It does not transform. It simply is. This stability is one of its defining characteristics. The dark matter halos around galaxies today look much the same as they did billions of years ago. Of course, halos can merge when galaxies collide, and they can grow as they capture more dark matter. But the dark matter itself does not change. The particles remain the same. They do not decay or transform into something else. This makes dark matter a constant presence throughout cosmic history. In a universe where almost everything changes, where stars are born and die, where galaxies merge and evolve, dark matter is the steady background, the unchanging stage on which the drama of the cosmos unfolds. The mysteries of dark matter inspire new generations of scientists. Every year, young people around the world choose to study physics, astronomy, and cosmology, drawn by the mystery of dark matter. They want to be the ones who finally solve it, who discover what dark matter is made of, who build the experiment or make the observation that unlocks the secret. This inspiration is one of the great gifts of unsolved problems in science. They capture the imagination. They show that there is still so much we do not know. They prove that science is not finished, that there are still frontiers to explore. still questions to answer, still mysteries to unravel. Dark matter is a beacon for curiosity. It invites us to look deeper, to think harder, to build better instruments, to ask bolder questions. And in pursuing it, we learn not just about dark matter, but about the universe as a whole, about gravity, about particles, about the birth and evolution of cosmic structure. The journey toward understanding dark matter is as valuable as the destination. Dark matter connects the very small to the very large. One of the fascinating aspects of dark matter research is how it bridges vastly different scales. On one end, particle physicists are trying to understand dark matter at the smallest scales. What particles is it made of? How do they interact? What are their properties? This is the realm of the very small. Subatomic, quantum. On the other end, cosmologists are studying dark matter at the largest scales. How does it shape the cosmic web? How did it influence the formation of the first galaxies? How does it affect the expansion of the universe? This is the realm of the very large, galactic, cosmic. And yet, these two ends are connected. The properties of dark matter particles determine how dark matter behaves on cosmic scales, and the observations of cosmic structure constrain what the particles can be. To understand dark matter fully, we need both perspectives. We need the particle physicists and the cosmologists working together. We need to connect the microcosm and the macrocosm. This is one of the beauties of modern science. The smallest and largest scales are not separate. They are part of a single, unified story. And dark matter is a key thread in that story. Dark matter is patient. It waits to be discovered. One of the most humbling aspects of the dark matter mystery is how long it has eluded us. Decades of searching, countless experiments, brilliant minds devoting their careers to the puzzle, and still, we do not have the answer. Dark matter is patient. It does not reveal itself easily. It challenges us to think more deeply, to build better instruments, to look in new places. But this patience is not frustrating, it is inspiring. It reminds us that the universe does not owe us answers. That knowledge must be earned through hard work, creativity, and persistence. Every experiment that does not find dark matter still teaches us something. It rules out possibilities. It narrows the search. It guides the next generation of experiments. Science is a long game. Some puzzles take decades or even centuries to solve. Dark matter might be one of them. But when we do finally understand it, the achievement will be all the greater, because we will have earned it. Dark matter teaches us humility in the face of the cosmos. There is something deeply humbling about dark matter. It shows us that for all our intelligence, for all our technology, for all our theories and equations, there is still so much we do not know. We cannot even identify what makes up most of the matter in the universe. This is not a failure. It is a reminder of our place in the grand scheme of things. We are small. Our knowledge is limited. Our understanding is incomplete. But we are trying. We are asking questions. We are searching for answers. And in that search, we find our humanity, our curiosity, our determination to understand, even when understanding seems impossibly distant. Dark matter reminds us that the universe is larger and stranger than we can fully grasp, that there are mysteries that may take generations to solve, and that is okay. We do not need to know everything today. We can be patient. We can appreciate the mystery. We can rest in the unknown, knowing that others will continue the search long after we are gone. The invisible universe is as real as the visible one. When we think about reality, we tend to focus on what we can see and touch. The solid earth beneath our feet, the bright sun in the sky, the stars at night. These things feel real because we can perceive them directly. But dark matter is just as real. It has mass. It has gravity. It shapes the universe. It is not an abstraction or a theoretical construct. It is a physical presence. The fact that we cannot see it does not make it less real. There are many things we cannot see that are nonetheless real. Gravity, magnetic fields, radio waves, the inside of the Earth. We infer their existence from their effects, and we do the same with dark matter. We see how it bends light, how it holds galaxies together, how it shapes the cosmic web. The evidence is overwhelming. So when you think about the universe, remember that the invisible is just as much a part of reality as the visible. Dark matter is out there. It is real. It is shaping the cosmos, even as you read these words. The universe is richer and more complex than our eyes alone can reveal. And that is a beautiful thing. Dark matter might reveal itself in unexpected ways. One of the exciting possibilities is that we might discover dark matter in a way we do not yet anticipate. Science has a long history of unexpected discoveries, of finding things we were not looking for, of stumbling upon answers while asking different questions. Dark matter might be the same. Perhaps a new telescope will detect a signal we did not predict. Perhaps a particle accelerator will produce an unexpected result that turns out to be related to dark matter. Perhaps an astronomical observation will reveal a pattern that only makes sense if dark matter has properties we had not considered. The universe is full of surprises, and dark matter might surprise us yet. This uncertainty is part of what makes science exciting. We do not know where the next breakthrough will come from. We do not know what form the answer will take. All we can do is keep searching, keep experimenting, keep observing, and remain open to the unexpected. The solution to the dark matter puzzle might be closer than we think, or it might be hiding in plain sight, waiting for us to look at it in the right way. The story of dark matter is still being written. We are living in a time of discovery. The dark matter mystery is one of the great scientific stories of our era, and it is still unfolding. Future historians will look back at this time and see it as a pivotal moment. The moment when humanity grappled with the reality that most of the universe is invisible. The moment when we pushed the boundaries of knowledge in search of an answer. We do not yet know how this story will end. Will we discover dark matter particles in our lifetime? Will it take another generation, another century? We do not know. But we know that the search will continue. That scientists will keep asking questions. That new experiments will be built. That new theories will be proposed. The story is not over. It is still being written. And we are part of it. Every observation, every experiment, every theory is a page in this story. And one day, someone will write the final chapter. Someone will discover what dark matter truly is. And that discovery will be one of the greatest triumphs in the history of science. Until then, we wait, we search, and we marvel at the mystery. Dark matter connects us to the ancient questions of philosophy. The mystery of dark matter is not just a scientific puzzle. It touches on ancient philosophical questions. What is the nature of reality? What exists beyond what we can perceive? How much can we truly know about the universe? These are questions that philosophers have pondered for thousands of years, and dark matter brings them into sharp focus. In a sense, dark matter is a modern echo of ancient debates about appearance and reality. Plato's allegory of the cave suggested that what we perceive is only a shadow of true reality. Dark matter tells us something similar. What we see, the stars and galaxies, is only a shadow of the full reality. The substance, the majority of the matter, is hidden from view. This intersection of science and philosophy is profound. It reminds us that science is not separate from the broader human quest for understanding. It is part of it. The same curiosity that drove ancient philosophers to question the nature of reality drives modern scientists to search for dark matter. We are all seekers, all trying to understand the world around us. And dark matter is one of the great mysteries that unites us across time. The universe operates on principles we are still discovering. Every law of physics, every equation, every theory is a human attempt to describe how the universe works, and we have been remarkably successful. We can predict the motion of planets, we can understand the fusion reactions in stars, we can trace the expansion of the universe back to the Big Bang, but dark matter reminds us that we do not have the complete picture yet. There may be principles, laws, or forces that we have not yet discovered. The universe may operate in ways we do not fully understand. Dark matter might be governed by physics we have not yet written down. And that is exciting. It means there is more to discover, more to learn, more to understand. Minutes. Science is not a static body of knowledge. It is a living, evolving process. Each generation builds on the work of the previous one. Each discovery opens new questions. And dark matter is one of those questions. It challenges us to think beyond what we know, to imagine new possibilities, to explore the unknown with open minds and careful methods. Dark matter may be the key to understanding the fate of the universe. The universe is expanding. We know this from observations of distant galaxies. But will it expand forever? Or will it eventually stop and collapse back on itself? The answer depends on the total amount of matter and energy in the universe, and dark matter is a crucial part of that calculation. If there is enough matter, including dark matter, the expansion could slow down and eventually reverse. The universe would collapse in a big crunch. If there is not enough, the universe will expand forever, growing colder and more diffuse over time, until all stars burn out and the cosmos fades into darkness. Current observations suggest the expansion is accelerating, driven by dark energy. But dark matter still plays a role in the dynamics. Understanding dark matter helps us understand the fate of everything. It is part of the cosmic balance sheet, part of the equation that determines whether the universe will end in fire or ice. In this sense, dark matter is not just a curiosity. It is essential to understanding the ultimate destiny of the cosmos. We are made of the same material as the stars, but dark matter is something else. When Carl Sagan said, "We are made of star stuff," he was referring to the fact that the atoms in our bodies were forged in the nuclear furnaces of stars. The carbon, oxygen, nitrogen, and other elements that make up our cells were created in stellar cores and scattered into space when stars died. We are literally made of stardust. But dark matter is not star stuff. It is something else entirely. It is not made of atoms. It does not participate in the chemistry of life. It is a different kind of matter, and yet it is intimately connected to our existence. Without dark matter, stars might never have formed. Galaxies might not exist. We would not be here to wonder about it. So while we are made of star stuff, our existence depends on dark matter. We are children of both the visible and invisible universe, products of a cosmos that is far more complex and mysterious than we once imagined. And that is a humbling and wondrous thought. The search for dark matter is a testament to human persistence. For decades, scientists have been searching for dark matter particles, building detectors, running experiments, analyzing data. And so far, the particles have eluded us. Many experiments have come up empty. Many theories have been ruled out. It would be easy to become discouraged, to give up, to move on to other questions. But scientists do not give up. They persist. They refine their techniques. They build more sensitive detectors. They try new approaches. This persistence is one of the defining characteristics of science. The willingness to keep searching, even when the answer seems impossibly distant. The faith that if we keep asking questions, keep gathering data, keep thinking creatively, we will eventually find the truth. This persistence is inspiring. It shows what humans are capable of when we commit ourselves to a goal, when we refuse to be defeated by difficulty, when we embrace the challenge and see it through, no matter how long it takes. The search for dark matter is a story of human determination. And whether we find the answer tomorrow or 100 years from now, that determination is something to admire. Dark matter is a reminder that wonder is inexhaustible. No matter how much we learn, there is always more to discover. No matter how many mysteries we solve, new ones emerge. The universe is not a finite puzzle that we will one day complete. It is an infinite source of wonder, and dark matter is a perfect example of this. 50 years ago, most scientists did not even know dark matter existed. Now it is one of the central mysteries of cosmology. Who knows what mysteries await us 50 years from now? What new phenomena will we discover? What new questions will we ask? The universe is vast and ancient and strange, and we have only just begun to explore it. This inexhaustibility of wonder is a gift. It means we will never run out of things to marvel at, never run out of questions to ask, never run out of horizons to explore. Dark matter is one horizon, but beyond it lie others, endless mysteries, waiting to be uncovered, and that is a beautiful thought. The universe whispers to us through dark matter. In a way, dark matter is the universe trying to tell us something. It is a message written in gravity and motion. In the rotation of galaxies and the bending of light, the universe is saying, there is more here than you realize. Look deeper, think harder. Do not be satisfied with easy answers. We are listening. We are trying to decipher the message. And slowly, piece by piece, we are learning to read it. Every observation, every experiment, every calculation brings us closer to understanding what the universe is trying to say. Dark matter is a whisper from the cosmos, a hint of deeper truths, and we are learning to hear it. This dialogue between humanity and the universe is one of the most profound aspects of science. We ask questions, and the universe answers. Not always clearly, not always quickly, but it answers. And in those answers, we find not just knowledge, but meaning, a sense of connection to something vast and timeless and beautiful. Dark matter is everywhere, yet it leaves us untouched. This is one of the most paradoxical aspects of dark matter. It surrounds us, it flows through us, it is part of the fabric of reality. And yet we never feel it. It does not affect our daily lives. It does not influence the weather, or the growth of plants, or the motion of cars. It exists in a parallel realm, present but intangible. This separation is both strange and comforting. Strange because it means we are immersed in something vast and invisible. Comforting because it means we are safe. Dark matter is not a threat. It is not something to fear. It is simply there, a quiet presence, an invisible foundation. In a universe that can seem chaotic and dangerous, there is something peaceful about dark matter. It does its work silently. It holds galaxies together without fanfare. It shapes the cosmos without violence. It is a reminder that not all powerful forces are destructive. Some are constructive. Some are gentle. Some work in silence to create beauty and order. The night sky is a doorway to the invisible. When you look up at the stars, you are seeing only the tiniest fraction of what is really there. For every point of light, there is a vast halo of dark matter. For every galaxy, an invisible scaffolding. The night sky is a doorway to a hidden universe, a realm that exists beyond the reach of our eyes, but is nonetheless real. This thought can transform the way you see the stars. They are not isolated points of light. They are beacons, shining from within vast, invisible structures. They are the visible tips of icebergs, most of which lie hidden beneath the surface. When you gaze at the Milky Way, you are seeing the luminous edge of a dark matter halo that extends far beyond the stars. The night sky, then, is an invitation to look deeper, to imagine what lies beyond the visible, to wonder about the hidden dimensions of reality. It is a reminder that the universe is more than it appears, that there are layers upon layers of existence, most of which we have yet to explore. Dark matter will be with us until the end of time. As the universe ages, stars will eventually burn out, galaxies will drift apart, the cosmos will grow cold and dark, but dark matter will remain. It does not burn, it does not fade, it is eternal on cosmic timescales. Long after the last star has died, dark matter will still be there, a silent presence in an empty universe. This permanence is profound. It means that dark matter is not just a temporary feature of the cosmos. It is a fundamental, enduring component. It was there at the beginning. It is here now. And it will be there at the end, if there is an end. In this sense, dark matter is the most stable thing in the universe. More stable than stars, more stable than galaxies, more stable than even atoms, which can be torn apart given enough energy. Dark matter endures, and in its endurance, it is a kind of cosmic constant, a thread that runs through all of time. The fact that we exist is connected to the properties of dark matter. This is a profound thought. The universe we live in, with its galaxies and stars and planets, exists because dark matter has the properties it does. If dark matter interacted more strongly with itself, it might have collapsed into dense clumps, leaving no room for galaxies to form. If it interacted less, structure might not have formed at all. If there were more dark matter, the universe might have collapsed back on itself long ago. If there were less, galaxies might never have held together. The amount and behavior of dark matter are finely tuned to allow the universe we see. This fine-tuning raises deep questions. Is it a coincidence? Is it a necessity? Is it evidence of something deeper about the nature of reality? We do not know, but what we do know is that we live in a universe where the invisible scaffolding of dark matter has made it possible for stars to shine, for planets to form, and for life to exist. In this sense, we are intimately connected to the mystery. We are products of the same cosmic forces that created dark matter and wove it into the fabric of space. Dark matter surrounds us, yet we remain safe. It is natural to wonder, if dark matter is all around us, passing through us, is it dangerous? The answer is no. Dark matter is completely harmless. It does not interact with our bodies. It does not affect our cells or our atoms. It does not carry energy in a way that could harm us. Billions of dark matter particles might pass through your body every second, but they leave no trace. They do not deposit energy. They do not ionize molecules. They simply pass through, like ghosts moving through a wall. This is part of what makes dark matter so difficult to detect. It is invisible not just to our eyes, but to every biological and technological system we have. We are safe in our ocean of dark matter. It shapes the universe, but it does not touch us. It is a benign presence, a silent companion, always there, never noticed. Dark matter has been part of the universe since the beginning. From the earliest moments after the Big Bang, dark matter has been a fundamental component of the cosmos. It survived the hot, dense plasma of the early universe. It persisted through the formation of the first atoms. It was there when the first stars ignited, and it will be there long after the last stars fade. Dark matter is ancient, primordial. It carries with it the memory of the early universe. By studying dark matter, we are studying the conditions that existed billions of years ago. We are probing the fundamental laws that govern the birth of space and time. Dark matter is a link to the past, a relic of creation. And it is also a promise of the future. As long as the universe endures, dark matter will be there, shaping structure, guiding the evolution of galaxies, providing the invisible foundation upon which everything else rests. The search for dark matter is a story of human ingenuity. Over the years, scientists have devised incredibly creative ways to search for dark matter. They have built detectors deep underground, shielded from cosmic rays by miles of rock. They have cooled materials to temperatures colder than outer space. They have analyzed the orbits of stars with exquisite precision. They have mapped the light from billions of galaxies. They have smashed particles together at nearly the speed of light. Each of these efforts represents a triumph of human ingenuity, a demonstration of what we can achieve when we set our minds to a problem. The search for dark matter has driven innovation in technology, in data analysis, in theoretical physics. It has brought together scientists from around the world working toward a common goal. Even if we have not yet found dark matter particles directly, the journey has been valuable. We have learned so much about the universe, about how galaxies form, about the structure of space-time, about the limits of our current theories. The search itself is a testament to the power of curiosity and the resilience of the human spirit. Dark matter reminds us that the universe is full of surprises. For most of human history, we believed that what we could see was all there was: the stars, the planets, the galaxies. We thought we understood the contents of the universe, but dark matter showed us we were wrong. The majority of matter is invisible, hidden, waiting to be discovered. This is a powerful reminder. The universe is not obligated to be simple or intuitive. It does not have to make sense in terms of our everyday experience. It can be strange and surprising. It can be strange and surprising. And that is part of what makes it wonderful. Every discovery, every new piece of the puzzle reveals that reality is richer and more complex than we imagined. Dark matter is one of those surprises. It challenges our assumptions. It forces us to think in new ways. And it reminds us that there is always more to learn. No matter how much we discover, there will always be mysteries waiting. The universe is vast, and we have only just begun to explore it. The silence of dark matter is profound. Think about it for a moment. Most of the matter in the universe makes no sound, emits no light, generates no heat. It is utterly silent. It exists in a state of quietude that is absolute. While stars explode and galaxies collide and black holes roar with the energy of infalling matter, dark matter remains still, unperturbed, a silent witness to the drama of the cosmos. There is something almost meditative about this silence. In a universe filled with energy and motion, dark matter is the calm center, the quiet background. It does not shout for attention. It does not demand to be noticed. It simply is, and in its silence, it holds the universe together. Perhaps there is a lesson here, that the most important things are not always the loudest, that strength can be quiet, that presence does not require fanfare. Dark matter shapes the cosmos not through spectacle, but through steady, patient gravity. It is the foundation upon which everything else rests, and it does its work in silence. Imagine the universe without dark matter. Try to picture it. A universe where galaxies do not hold together, where stars drift apart, where structure does not form. It would be a very different place. Dim, sparse, empty, isolated stars, separated by vast distances, slowly burning out. No clusters, no cosmic web, no Milky Way, no sun, no Earth. This thought experiment helps us appreciate what dark matter has given us. It is not just an abstract scientific puzzle. It is the reason our universe is rich and structured and full of light. It is the reason we exist. Without dark matter, the cosmos would be unrecognizable, a vast, lonely expanse, a universe without homes for life. When you look up at the night sky, you are seeing the visible tip of a much larger structure, a structure made possible by dark matter. Every star, every galaxy, every cluster. They exist because of the invisible scaffolding that surrounds them. We live in a universe of light and shadow, and the shadow, though unseen, is just as important as the light. The mystery of dark matter invites wonder. Science is often seen as a process of finding answers, and it is. But it is also a process of asking better questions, of uncovering deeper mysteries. Dark matter is one of those mysteries. It invites us to wonder, to marvel, to stand in awe of a universe that can surprise us so completely. Wonder is at the heart of science. It is what drives us to explore, to experiment, to observe, to question. And dark matter, in its invisibility and mystery, is a perfect source of wonder. It shows us that the universe is not fully known, that there are still secrets to uncover, still frontiers to cross. And that sense of wonder is not just for scientists. It is for everyone. Anyone can look up at the sky and know that most of what shapes those stars and galaxies is invisible, hidden, mysterious. Anyone can feel the awe of living in a universe where the unseen is more vast than the seen. This is a gift, a reminder that we are part of something much larger than ourselves. Dark matter is a thread in the fabric of existence. If you could see the universe in its entirety, you would see that dark matter is woven into everything. It is not separate from the visible universe. It is part of it. Every galaxy is embedded in dark matter. Every cluster is held together by it. The cosmic web is drawn by it. Dark matter is a thread running through the fabric of existence, binding everything together. This interconnectedness is beautiful. Nothing in the universe is isolated. Everything is part of a greater whole, and dark matter is one of the threads that makes this whole possible. It connects the smallest galaxies to the largest clusters. It links the past to the present. It ties the very small to the very large. We are part of this tapestry as well, made of atoms forged in stars, living on a planet that orbits a star that exists because of dark matter. We are not observers, standing outside the universe, looking in. We are participants. We are part of the story, and dark matter is part of our story, too. Let yourself drift into the vastness of it all. As you rest here, breathing slowly, let your mind wander through the cosmos. Imagine the dark matter halos surrounding galaxies. Picture the invisible filaments stretching across space, connecting clusters and superclusters. See the vast, silent ocean of dark matter that fills the universe. You are floating in this ocean, even now. Dark matter flows around you, through you. It is part of the fabric of reality, and you are part of that same fabric, made of stardust, held by gravity, connected to everything that is and ever was. There is no need to understand it fully, no need to solve the mystery tonight. Just rest in the knowledge that the universe is vast and strange and beautiful, that it holds secrets we have not yet uncovered, and that you are a part of this grand unfolding story. A small part, perhaps, but a real part, a thread in the tapestry. The universe is patient, and so are we. The search for dark matter will continue. Tomorrow, next year, for decades to come, scientists will keep building detectors, running simulations, analyzing data, asking questions, and one day, perhaps, we will find the answer. We will discover what dark matter is made of. We will understand its properties. We will solve the mystery. But even if that day takes a long time to arrive, the journey is worth it. Because in searching for dark matter, we learn about the universe. We push the boundaries of knowledge. We develop new technologies. We inspire future generations. We remind ourselves that there are still wonders waiting to be discovered. The universe is patient. It has waited billions of years. It can wait a little longer, and so can we. We can rest in the mystery. We can let it surround us. We can appreciate the beauty of not knowing, of being small in a vast, mysterious cosmos, of being part of something so much larger than ourselves. Dark matter is a gift to our curiosity. Think of it this way. The universe could have been simple. It could have been made of only the matter we can see. It could have been easy to understand. But it is not. It is complex, layered, full of hidden depths, and that complexity is a gift. It gives us something to explore, something to wonder about, something to strive to understand. Dark matter is one of those gifts. It challenges us. It invites us to look deeper, to think harder, to reach farther, and in doing so, it makes us better scientists, better thinkers, better explorers. It reminds us that the universe is not here to be simple or convenient. It is here to be discovered. And we are here to discover it. That is part of what makes us human. The desire to know, to understand, to explore. Dark matter speaks to that desire. It calls to us from the shadows. It says, "There is more, come and find it." And so, dear listener, our journey through the invisible universe comes to a gentle close. We have wandered together through the realm of dark matter, that hidden ocean in which all galaxies float. We have glimpsed its effects, though not the substance itself. We have marveled at its mystery and its power. We have learned that most of the universe is made of something we cannot see, that the stars and galaxies we love are only a small fraction of what exists, that beneath the visible surface lies a vast, invisible depth, a scaffolding of dark matter that holds everything together. This knowledge is humbling. It reminds us of our place in the cosmos. We are small. We know very little. We see only a tiny sliver of reality. But we are curious. We ask questions. We search for answers. And in that search, we find meaning. We find wonder. We find connection to something greater than ourselves. As you lie here, let the mystery of dark matter wash over you. Let it be a source of calm, of peace. You do not need to understand it. You do not need to solve it. Just know that it is there, that it shapes the universe, that it is part of the grand story of existence, and that you, too, are part of that story. Picture yourself floating in space, surrounded by dark matter, invisible particles flowing past you, through you. You are immersed in the hidden universe, the silent ocean, the dark foundation of all that is. And it is peaceful, it is calm, it is vast and timeless and eternal. The stars shine above you, distant galaxies glow in the darkness, and beneath it all, unseen, but ever present, is the dark matter, holding everything together, shaping the cosmos, guiding the dance of galaxies and the birth of stars. It is the quiet strength of the universe, and it surrounds you now. Let yourself sink into that quietness, into that stillness. The universe is ancient. It is vast. It has seen the birth and death of countless stars. It has shaped galaxies and woven the cosmic web. And it will continue long after we are gone. We are brief flickers in the vastness of time, but we are here now, and that is enough. Breathe deeply. Feel the calm. Know that you are part of something much larger, something mysterious and beautiful and profound. You are made of atoms, forged in stars. You live on a world shaped by gravity. You exist in a universe held together by dark matter. You are connected to it all. And now, as your thoughts drift gently away, as your breath slows and your body relaxes, let the darkness of dark matter be a comfort, not a darkness to fear, but a darkness to rest in. The soft, silent, invisible ocean that holds the universe together, let it hold you, too. Close your eyes. Let go of questions. Let go of wondering. Just rest, drift, sink into the quiet, into the calm, into the vast, gentle mystery of the cosmos. The stars will keep shining. The galaxies will keep turning. The dark matter will keep holding everything together. And you, dear listener, can rest. You can sleep. You can let the universe carry you into stillness, into peace, into dreams. Good night. Sleep well. And may the invisible ocean of the cosmos cradle you gently through the night.